Hello everybody, getting ready to do classwork section 9, SAT Math Level 2 Prep. And for today's lesson, you got 10 points to go into your notebook, part 1, rational functions. And you got 18 points to go on your classwork sheet, which you should have in front of you. Name, date, period, students in my class, due date for onliners and homeschool. And for today's lesson, page 1, a notebook entry here. A function is a rational function if it is the ratio of two polynomials. So for example, r of x equals p of x over q of x. For level 2 math subject test, you should know about the occurrence of vertical asymptotes and holes in graphs of rational functions. A vertical asymptote is a vertical line, such as x equals a, where a is a 0 of q of x, but is not of q of x, but not a 0 of p of x, okay? The value a is not in the domain of R, and the y-coordinate gets infinitely larger in either the positive or negative direction as x gets smaller. No, as x gets closer to a. There it is there. This creates a discontinuity or a break in the graph at x equals a. A hole is a second type of discontinuity in a graph. This occurs at a value of x that makes both the numerator p of x and the denominator q of x equal to 0. The y-coordinate of a hole is a functional value after the common factor has been divided out. So let's get into some examples of these situations. Consider y equals x plus 4x minus 3. So, and then here's a graph of that here. As x gets closer to 3, which is here, 1, 2, 3, the denominator gets closer to 0, x equals 3, it gets closer to 0, but the numerator doesn't. The numerator does not get close to 0. The graph of this function has x equals 3 as a vertical asymptote. So here is your vertical asymptote for that. And then b here. Consider y equals x plus 1 over x squared minus 1. Factor the denominator to get y equals x plus 1 over x plus 1 over x minus 1. Since y is undefined when x equals 1 or negative 1, these are the values that must be checked for holes in vertical asymptotes. As x gets closer to 1, the denominator gets closer to 0, but the numerator doesn't. Therefore, x equals 1 is a vertical asymptote. So as x gets closer to 1, say up there, the denominator gets closer to 0, but the numerator doesn't. Again, same, kind of like the one before. Therefore, x equals 1 would be a vertical asymptote if x does not equal 1. The factor x plus 1 in the numerator and the denominator can be divided out so that y equals 1 over x minus 1. In other words, the functions y equals x plus 1 x squared minus 1 and y equals 1 over x minus 1 are identical except when x equals negative 1. If you substitute x equals negative 1 into y equals 1 over x minus 1, you get y equals negative 1/2. So there are differences there and things to consider. So in other words, there is a hole at the point of negative 1 and negative 1/2. So negative 1 and negative 1/2 would be right there, would be your hole. In general, a graphing calculator will not show a hole because there is no pixel at that point. The hole is shown here in the graph. Your hole is right there. Because we know by discussion that there is a hole when x equals negative 1, and we set the window to be sure that the calculator would attempt to graph that point. Never attempt to identify a whole only by looking at the graph of rational function. So if you need students, if you need to review rational functions, I have review packets available for you. So go ahead and contact me for those. So another aspect of rational functions that may appear on the level 2 math subject test concerns the behavior of f of x as x becomes infinitely larger in either the positive or negative direction, limits at infinity. While there are algebraic explanations of this behavior, it is more useful to analyze it in a more intuitive fashion. This is accomplished in an example. So if r of x equals 3x squared minus 2x plus 4 over x cubed plus x minus 5, what value does r of x approach as x gets infinitely larger? So observe that the highest power of x will dominate the numerator and the denominator for every large value of x. This means that the larger x is, the more the numerator looks like 3x squared, and the more the denominator looks like x cubed. In other words, as x gets larger, we have 3x squared over x cubed will become 3 over x, which approaches 0 in that case. As x would get larger here, this number would get smaller. D, if r of x equals 3x squared minus 2x plus 4 over x squared plus x minus 5, what value does r of x approach as x gets infinitely larger? So in this case, r of x equals 3x squared over x squared equals 3. As x gets larger in a positive or negative direction, E of r of x equals 3x cubed minus 2x plus 4 over x squared plus x minus 5, what value does r of x approach as x gets infinitely larger? So in that situation, the highest powers of x dominate for large values of x. So in this case, r of x will equal 3x cubed over x squared, which will reduce to 3x. Since this later quantity simply gets larger in the positive direction as x gets larger, it is said that r of x approaches infinity, or positive infinity. Okay, as we move on now into F here, if r of x equals 3x cubed minus 2x plus 4 over x squared plus x minus 5, what value does r of x approach as x gets infinitely smaller, meaning larger in the negative direction? So where does r of x approach? The analysis is similar to that in example E, except that as x gets infinitely smaller up here, 3x also gets smaller, meaning it approaches negative infinity. So that would be where to go, negative infinity. So for G, if r of x equals negative 3x cubed minus 2x plus 4 over x squared plus x minus 5, what value does r of x approach as x gets infinitely larger now? So where does r of x approach as x gets infinitely larger? In this case, r of x approximates negative 3x, so r gets infinitely smaller as x gets infinitely larger. And then h, if r of x equals 3x to the fourth minus 2x plus 4 over x squared plus x minus 5, what value does r of x approach as x gets infinitely smaller in this situation here? So this time r of x equals 3x squared. We cancel this out here. It will be 3x squared as x gets smaller, so r gets larger. In this case here, since 3x squared is greater than 0 for all of x not equaling 0. These examples illustrate the behavior of a rational function As x increases in the positive or negative direction, the behavior can be summarized as follows. If r of x equals p of x over q of x, and the leading coefficients, exponents of the largest powers of p and q, are am and bn, and if x approaches plus or minus infinity, then if the degree of p is less than the degree of q, r of x approaches 0. There is a horizontal asymptote, in this case y equals 0, meaning the x-axis. If the degree of p is equal to the degree of q, r of x approaches am over bm. There is a horizontal asymptote, in this case, of y equals am over bn. So we have two different conditions here, depending upon the degree of p and q. If the degree of p is greater than the degree of q, r of x approaches plus or minus infinity. This can be analyzed by remembering that a, the division of numbers with the same sign results in a positive number, and the division of numbers with opposite signs results in a negative number, and b, a negative number raised to an even power is positive, and a negative number raised to an odd power is negative. There is no horizontal asymptote in this case. You can also use a graphing calculator to guess or verify limits at infinity. Returning to example D, we are interested in determining what value r of x equals 3x squared minus 2x plus 4 over x squared plus x approaches as x gets larger. Enter the expression for r of x into y1 and set independent and table set, second window, to ask, and then enter table, second graph, delete existing entries, enter larger and larger values of x. For example, 10, 100, 1000 like here, and observe y1, and then y1 here settles on 3. The table screen for this activity is shown below. It should be clear from the entries for y1 that the expression gets closer to 3 as x gets larger. Although they are not rational functions, expressions that involve ratios of radicals can be analyzed in the same fashion. If f of x equals square root of x squared minus 3x plus 10 over x minus 2, what value does f of x approach as x gets infinitely larger in this situation here? As x gets larger, the numerator looks more like the square root of x squared, which equals absolute value of x, and the denominator looks more like x, so f of x would equal absolute value of x over x, which would equal x over x for x greater than 0. Therefore, as x gets infinitely larger, f of x approaches 1. So if f of x equals the square root of x squared minus 3x plus 10 over x minus 2, what value does f of x approach as x gets infinitely smaller? In this case, the denominator is negative, so f of x approaches negative 1, meaning as it approaches negative infinity. So absolute value of x equals negative x. When x is less than 0, f of x equals approximates the absolute value of x over x, which equals negative x over x, which equals negative 1, as x gets infinitely smaller. And that is your Section 9 SAT Math Level 2 preparation, animated PowerPoint math video at AOL.com for questions or course materials. Thank you very much.